Discover the powerful and precise world of steel plate bending through these captivating and high-tech industrial videos. The steel plate rolling process begins with precise preparation to ensure a high-quality cylindrical outcome. A flat steel plate, designed with slight excess length on both sides, is carefully positioned for processing. This excess length is critical to allow for accurate edge preparation, ensuring the plate can be rolled into a perfectly round shape. The edges of the plate are meticulously beveled to create precise weld preparations, a step that demands high accuracy to achieve a seamless final product. Once the beveling is complete, the plate is marked with precision to guide the cutting process. This is a high-precision task, ensuring that the resulting cylinder has a perfect round shape and consistent weld quality. He says, to facilitate smooth cutting, the plate is preheated to an optimal temperature, which prevents material stress and ensures clean cuts. During the cutting process, the excess length is trimmed off, and the weld edges are simultaneously formed, preparing the plate for rolling. The now accurately sized and beveled plate is ready to be fed into the advanced 3-roll Heisler plate rolling machine, a 320-ton powerhouse manufactured in Switzerland. This machine, equipped with immense capabilities, rolls the plate into a cylindrical shape with an external diameter of 2,076 millimeters. The rolling process is executed with precision to achieve the desired curvature without compromising the structural integrity of the steel. After rolling, the cylindrical shell is prepared for welding. The weld seams are joined using a highly productive submerged arc welding method, characterized by a high deposition rate. This technique employs 2 filler wires simultaneously, allowing the weld seam to be filled quickly and efficiently. A layer of flux powder covers the welding area to protect the weld pool, and any excess powder is collected for reuse, ensuring an environmentally conscious process. The welded seams are robust, ensuring the cylindrical shell maintains its structural strength for its intended application. In addition to rolling, the facility features a powerful press brake with a bending capacity of 3,000 tons over an 8,000 millimeters length, one of the heaviest in Europe, capable of exerting 800 tons of bending force per meter. This press brake is shown processing a 60 millimeters thick stainless steel plate, 7.2 meters in length, which is bent to a specific radius to meet precise project requirements. The machine's ability to handle such thick and long materials demonstrates its versatility and strength in forming complex shapes. As a final showcase, the rolling machine processes an impressive 43-ton steel plate, measuring 150 millimeters in thickness and 2,230 millimeters in width. This massive plate is rolled into a cylinder with a diameter of 5,000 millimeters, highlighting the machine's extraordinary capacity to handle heavy-duty tasks. The process, from edge preparation and cutting to rolling and welding, exemplifies precision, efficiency, and advanced engineering, delivering high-quality cylindrical steel components for demanding industrial applications. Each stage of the process, edge preparation, marking, heating, cutting, rolling, welding, and pressing, is executed with extreme precision and coordination, allowing for the fabrication of exceptionally large and high-quality cylindrical steel components. Halain. The process begins with the selection and preparation of steel pipes and plates. Steel pipes are cut to precise lengths using automated cutting machines. After cutting, each component is numbered and marked, which helps maintain full traceability and ensures correct assembly later in the process. Next, welding operations are carried out using both TIG and MIG welding techniques. These methods are chosen for their ability to produce clean, durable, and pressure-resistant joints. TIG welding is typically used for precision and fine detailing, while MIG welding provides strength and efficiency. Both the inner and outer surfaces of the joints are welded to ensure structural integrity under pressure. Once welding is complete, the various parts of the vessel undergo precise assembly. The cylindrical shell is aligned carefully with the end caps and other components. Accurate fitting is essential to ensure the vessel performs safely and reliably in demanding industrial environments. During the later stages of production, laser technology is employed for both marking and cutting. A laser engraving system is used to etch names, codes, or identifiers onto the tank lids. This not only provides identification, but also supports quality control and documentation. Meanwhile, laser cutting machines are used to create holes in the covers for future installation of pipes, valves, or sensors. These holes are made with high precision, minimizing the need for additional finishing. The outer contours of flat steel sheets are also shaped by laser cutting, ensuring clean edges and accurate dimensions. Additionally, the outer contour of flat steel plates is also shaped using a laser cutting machine, allowing for clean, accurate edges. Once cut, these steel sheets are fed into a 3-roll bending machine, where they are formed into cylindrical shapes to create the tank's body. The machine gradually bends the flat sheet into a perfect round form, preparing it for further welding and assembly. This bending process is crucial in forming the tank body before final assembly and welding. Throughout the process, Depressed applies strict quality standards in line with European regulations, ensuring that each product meets the needs of industries such as chemical, pharmaceutical, and food production. The production of a welded beam begins with the nesting process, where beam components are digitally arranged on steel plates to optimize material usage and minimize waste. This nesting layout is then transferred to the cutting machines. Once nesting is complete, the layout is sent to the cutting machine and the cutting process begins. CNC-controlled cutting equipment, such as plasma or Oxifuel cutters, precisely cuts the steel plates according to the nesting plan. The result is a set of individual plates shaped and sized as required for the beam's construction. These cut plates are then moved to the plate service center, where further processing begins. The first step here is grinding, which removes sharp edges, burrs, and surface imperfections from the cut parts. This is essential to ensure proper fit-up during welding and to improve the final weld quality. After grinding, the individual components are temporarily assembled in the tack welding stage. The web is positioned between two flanges, and tack welds are applied at intervals to hold everything in place. This ensures the parts are aligned correctly and remain stable during full welding. Next is the copping process, where parts of the flange or web are trimmed or shaped to allow clearance or fit for connections or intersections with other structural elements. This is typically done with cutting torches or machining tools. Once the structure has been tack welded and coped, the full welding process is carried out. In this phase, skilled welders or automated welding machines perform continuous welds along the length of the seams where the flanges meet the web. The welds must be strong, consistent, and meet structural standards. After welding, the beam undergoes gauging, also known as gouging. This involves the use of air carbon arc tools to clean up welds, remove any excess material, and ensure a smooth surface. This step also helps prepare areas that might require re-welding or inspection. Since welding can cause deformation, the beam is then subjected to straightening. Mechanical presses or rollers apply force to correct any warping and ensure that the beam remains within the specified tolerances. If mechanical straightening is insufficient, heat correction is performed. This involves applying controlled heat to certain areas to relieve stress and bring the beam back into alignment. The beam is then cleaned and prepared for the final check. The welded beam goes through a final inspection. Inspectors check for straightness, weld quality, dimensions, and surface finish. Any issues found are corrected before the beam is approved. Only beams that pass all criteria are accepted as finished products. Throughout the entire process, the Plate Service Center plays a central role in processing, handling, and preparing the steel components for each step. From cutting and grinding to welding and straightening, this centralized hub ensures efficient workflow and quality control. The production process at Vika Steel begins with reheating massive steel slabs in a furnace until they reach rolling temperature. Once heated, the slabs are transported to the rolling mill, where they undergo several passes through powerful rollers to reduce their thickness and achieve the required dimensions. These hot-rolled heavy plates are then cooled on a run-out table and cut to specific lengths. For sheet piles, selected plates are processed further. They are fed into a rolling line equipped with specialized rolls that gradually shape the steel into interlocking profiles. After forming, the sheet piles are cut, cooled, and stacked for delivery. Additionally, the facility produces cut shapes by Oxifuel or plasma cutting methods. Heavy plates are precisely marked and automatically cut into complex geometries based on customer specifications. The resulting steel parts are deburred and prepared for use in construction, machinery, or shipbuilding applications. Throughout the process, rigorous quality checks are performed to ensure that each product meets strict dimensional and mechanical standards. The beveling test begins by clamping a spherical metal blank into a hydraulic press forming die. The upper tool, designed to form the beveling, gradually lowers and contacts the outer edge of the blank. As pressure is applied, the material is pushed down and out, forming a curved edge along the perimeter. During this stage, the blank is continuously supported by the lower die to prevent wrinkling or material slippage. During the forming process, a steady force is applied to ensure that the beveling develops evenly. The beveling height increases as the upper tool is lowered in a controlled motion. Throughout the process, the operator closely monitors the deformation to assess the formability and behavior of the material under stress. When the beveling is reached, the resulting beveling edge is then visually inspected for cracks, wrinkles, or irregularities. This beveling test is used to assess the ductility of the metal and its ability to withstand edge deformation without failure. It also helps evaluate tool performance and process parameters for future manufacturing applications. The flanging process begins with a preformed dished end, which has an inside diameter of 4.5 meters before flanging. This component is positioned vertically on the rotary base of the flanging machine. An operator adjusts the alignment to ensure the dish is centered and stable before the operation starts. A robust forming roller slowly approaches the edge of the dish, while the dish rotates steadily. This roller gradually bends the outer circumference downward, forming the flange. The process is precisely controlled with hydraulic arms and adjustable pressure to prevent cracking or warping of the material. The roller continuously applies force along the rotating edge, maintaining even pressure to form a consistent and symmetrical flange profile. Throughout the operation, the dish's rotation speed and the roller's descent are coordinated to match the curvature required. The operator monitors the progress closely, making minor adjustments to the pressure and positioning as needed. The machine ensures uniform flanging even for large diameter parts by maintaining constant torque and feed rate. As the flange forms, its radius and vertical extension are checked to confirm it matches the required specifications. Once the desired profile is achieved, the forming roller retracts and the flanged dish is carefully removed from the machine. This cold-forming method used by the Fchin flanging machine ensures high precision and surface integrity, even for large, heavy steel-dished ends. CAH Bastile, a leading special steel producer, is pioneering the large-sized forging market by leveraging its extensive experience in manufacturing high-quality steels. At its heavy forging plant, CAH Bastile produces ingots up to 600 tons through an ultra-clean steel casting process, using a 150-ton electric arc furnace, vacuum degassing, and vacuum ingot casting. The facility is equipped with 2,000-ton, 4,000-ton, and Korea's largest 13,000-ton presses to produce a wide range of forged products, including the largest diameter forgings in Korea. The company operates a complete in-house system, covering every stage from casting and forging to heat treatment, inspection, and shipping. These capabilities enable CAH Bastile to deliver world-class quality and the shortest lead times. Its forged products serve critical industries such as power generation, nuclear, marine, and heavy machinery. With a strong R&D center and global certifications, CAH Bastile is establishing itself as a global leader in extra-large forgings and advanced material technology. The 60-ton electric arc furnace is a powerful steelmaking unit designed for melting scrap metal using high-temperature electric arcs generated between graphite electrodes. This furnace plays a central role in modern steel production by offering flexibility, efficiency, and reduced environmental impact. At the heart of the system are 3 large graphite electrodes that are gradually lowered into the furnace to create an intense arc between the tips and the metal charge. The generated heat reaches temperatures above 3,000 degrees Celsius, allowing for rapid melting of a wide range of steel scrap and additives. The furnace is equipped with a tilting mechanism to facilitate slag removal and molten steel tapping. It also features advanced control systems to regulate energy input, electrode positioning, and temperature monitoring, ensuring consistent steel quality and optimal power consumption. With a 60-ton capacity, this EAF can complete a melting cycle within 45 to 60 minutes, depending on the charge mix and operating conditions. It is commonly integrated into mini-mill setups and serves industries demanding high-grade alloy or carbon steel. Overall, the 60-ton EAF is a critical asset in sustainable steelmaking, enabling efficient recycling and high productivity in modern foundries. The spiral case for the Voith hydropower project is manufactured from Q345B steel with dimensions of 8,300 by 8,964 by 2,800 millimeters and a total weight of 21,924 kilograms. The production process involves several key steps: rough machining, finish machining, structural welding, assembly, straightening, and heat treatment to relieve internal stress. These steps ensure the required precision and mechanical strength for hydropower operation. After completing all processing and performance adjustments, the spiral case is thoroughly inspected for dimensional accuracy and weld quality. Finally, the completed unit is carefully loaded onto a trailer and secured for transportation to the hydropower construction site, a heavy-duty bending roll manufactured by Daido machinery, performing precision bending on a massive steel plate, a 4,500 millimeters wide plate with 70 millimeters thickness under 896-ton pressing force. The process begins with the raw plate being positioned between the rolls. With Daido's CNC bending roll technology, the upper rolls descend under hydraulic power, applying uniform pressure across the full width. The tremendous 896-ton compressive force gradually deforms the thick plate into a smooth arc. As the rolls advance, the plate is fed through, bending incrementally with high repeatability. The machine's CNC control ensures precise alignment and consistent curvature, even on such a large, thick plate. Hydraulic actuators synchronize roll movements to maintain the correct bending radius across the entire 4.5-meter width and stubborn 70 millimeters thickness. Once the plate passes fully through, a uniform cylindrical or curved section emerges. The result is a flawlessly bent steel plate, suitable for heavy industrial applications such as pressure vessels, storage tanks, or large structural frames. This level of bending on a plate this thick and wide demonstrates Daido machinery's ability to deliver high-precision forming with enormous tonnage capacity. In summary, the seamless orchestration of hydraulic force, CNC control, and mechanical robustness to transform an enormous flat plate into a precise curved section. The combination of 4,500 mm width, 70 mm thickness, and 896-ton press force underscores both the scale and accuracy of the operation. The Fchin 4-roll double-pinch bending machine is used to roll a 3/4 thick cone plate for a 2.00 mg elevated water storage tank. This CNC-controlled machine accommodates 12 feet rolls and operates on a 13 feet x 41 feet table, ensuring precise feeding and positioning. It can form both cones and cylinders with tight tolerances, minimizing welding and improving overall production quality. During operation, the plate is gradually fed through the rollers to form the desired cone shape. The double pinch design allows for better grip and control, enabling consistent and accurate results throughout the bending process. Landmark's 750-ton Bliss mechanical press is used to form a 1/4, approximately equals 6 mm, steel plate into the upper ball segment of a 250,000-gallon elevated spheroid storage tank. The process begins with a flat plate of precisely measured thickness, cleaned and prepared before forming. The plate is positioned beneath custom dies designed to create double-curved, spherical contours. As the press descends, it exerts up to 750 tons of force, carefully dishing the steel into the desired curvature. Landmark's equipment can handle plate thicknesses ranging from 3/16, approximately equals 4.8 mm, up to 3 inches, approximately equals 76 mm, enabling custom-formed shapes across a range of sizes. Samo laches. Throughout the operation, die alignment and lubrication are critical to ensure smooth metal flow and prevent wrinkles or cracking. After the first pass, the plate may be rotated or re-indexed to achieve uniform curvature. Final inspection verifies that tolerances and surface quality meet ASME U and R stamping requirements. This method produces precise, robust, spherical sections ideal for large elevated tanks, combining cold press forming accuracy with heavy-duty industrial scale. At voestalpine Tubulars in Kinberg, Austria, advanced wall thickness measurement systems ensure precise dimensional control of seamless steel tubes. The process involves two main types of sensors, the O-frame and the C-frame. The O-frame system features a 9-channel setup that enables double wall measurement. It encircles the tube and uses multiple ultrasonic transducers to measure the wall thickness at 9 different positions simultaneously. This provides a comprehensive cross-sectional profile of the tube and ensures uniformity around the circumference. The system detects even slight variations in thickness, enabling real-time quality control and adjustments during the production process. Complementing this is the C-frame system, equipped with a single-channel sensor designed for mass measurement. This frame is positioned to measure thickness along a specific line of the tube. The C-frame's high-resolution data contributes to calculating the average wall thickness and mass per unit length of the product. This information is critical for meeting customer specifications and maintaining tight manufacturing tolerances. These non-contact, automated measurement systems play a crucial role in quality assurance. They allow for continuous monitoring without interrupting production, ensuring every tube meets the highest standards of dimensional accuracy and mechanical performance before it proceeds to the next stage of processing or shipment.